Hello everybody to our presentation of this year Corona CIRP. Normally we would have been in Munich. Unfortunately, as we all know, it's impossible to host you here. And as one of the co-hosts, it's my pleasure to give you at least a presentation here from Munich within our virtual CIRP. Title of our contribution is Influence of Non-Proportional Load Path and Change in Loading Direction on the Failure Mode of Sheet Metals. So it's in the field of failure prediction and with the additional point of taking into account the anisotropy of the material behavior. I also want to mention my co-authors. It's Norz, Matthias Eder, and also our CIRP member Hoffmann. Okay, let's start. Outline is as usual, starting with introduction. Then I want to present the experimental setup, give you some results, and then based on the results, a prediction model also taking into account anisotropy for the prediction of failure with non-proportional load path. Okay, to warm up, we know non-proportional load paths are an important task in the prediction of sheet metal forming simulations. Here, based on a schematic view for a sidewall panel, we know that when we have ongoing operations like here, over here to here, that there can result a non-proportional load path. And we know it's not possible to predict this material behavior with a conventional linear FLC, and we need more complex models which are available. There can be stress-based, the EMFC, also our GFLC model, what was developed at our institute and I presented in CIRP Konferenz 2012. So, one topic which is not taken into account so far is the question of anisotropy. We know, based on change in the substructure of the material, that we have anisotropic behavior. We know that we have some different yield strength when changing the loading direction with respect to the rolling direction. So this is one of the main objectives of this work. Also to prove it experimentally what happens when we have a non-proportional load path in addition with the change of the loading direction with respect to rolling direction. Therefore, it's necessary to do some tests, and especially for the FLC, we start with the usual test equipment, this Nakajima test. So we have used the conventional Nakajima test with the die, blank holder, the spherical punch, and you know that it's possible to change the ratio of minor and major strain just by changing the size of the specimens. Here, for our material, with this absolutely common steel material, a microalloy 340 steel, where we know that we have some slight differences also for the FLC, the linear FLC, with respect to the rolling directions. Now, as I mentioned some minutes ago, is our main goal to describe the behavior when changing the loading direction within a non-proportional load path. There, it's necessary to have a suitable test equipment to realize this, and this is available at our institute. It's an oversized Marciniak test, as you can see here, with the big dimensions of 1,590 to 1,300 millimeters. And the dimensions are chosen so that even when we have uniaxial strain, it's possible to cut out secondary specimens where we can also totally can change it with respect to the rolling direction. Here we see also the names for it. We have an initial forming step and a post-forming step. And when there is now 0, 45, and 90 for simplicity, I just always mean with respect to the rolling direction. So IFO PF45 means 0 degrees for the first step and 45 degrees with rolling direction for the second step. Okay, we didn't expect a big difference, but a remarkable difference, and performed the experiments. And then really a surprising effect came out. Please have a look here. So here in our strain diagram, this is the initial forming step of around 50% of the FLC in uniaxial direction. And with the gray curve, where it's 0-0 combination, we have the well-known material behavior. Here, absolutely clear, no difference. And then when changing in plane strain, we reduce formability, and we go to biaxial strain, we are winning formability. But now have a look for 45 and 90 degrees. I'll start with 90 degrees. It's the red curve. The only difference, we start preforming 0 degrees, and then just turn around by 90 degrees, and then do the second step. And you see here the totally different material behavior. That we are losing much formability just by changing the rolling direction of the second step. For 45, is somewhere in between. Here it's also in uniaxial. We are losing much formability. In plane strain, it's not so critical. And when we go to biaxial direction, it's nearly the same. We can also see it with the heights we can reach, that here the 0-0, here 0-45, and 0-90. These are these 3 points. So I want to summarize this as the fundamental motivation of the paper, that a change in loading direction surprisingly led to a significantly influence of the remaining formability for pre-strained specimens. And due to the fact that the stresses are probably the same, we can directly find out that this effect cannot be captured by established models which are published and used, like the EMFC, PEPS, or also our phenomenological GFLC model. So now we go more in detail. For the analysis, we have seen here the 50% preformed, but also we wanted to prove how severe this effect is when we have a reduced amount of preforming. That means around 25% with respect to the FLC. So we have 2 different preforming states which are investigated in the following. Here now we see the behavior with 50% uniaxial preformed specimen, 0-0 combination, so the classical one. We see the start of diffuse necking, and then we go to the plane strain behavior, where we know that with this point we have some microvoids which can occur because of the 3-dimensional strain state, and finally we have the start of localized necking starting out of the mid of the specimen. So this is well-known behavior. And now let's compare with this significantly reduced formability in the 0-90 combination. It means 50% uniaxial preformed, and second step in 90 degrees. It's the red curve. You can directly see here that there is a big difference. When we have a view on the evolution, we see here this surprising effect that we have some kind of localization in shear direction directly after start of the second forming step. So this is, we see directly no change to plane strain, and like a smooth, ductile shear fracture. So also in comparison to the classical one, no start out of the specimen mid, and really a totally different strain behavior, a little bit comparable to materials with a negative strain rate sensitivity, which is here not the case. Okay. Now, let's compare it also for the second group of specimen, where we have used a preforming step of only 25%. So with 25% preforming, we don't see this effect of shear localization. Always same behavior, start of diffuse necking and then localized necking out of the middle of the specimen. And when having the big pre-strain of 50%, here also in 45 and 90 degrees, we have the totally different failure behavior. So in the following, we describe this classical one, change to plane strain with failure mode 1, and this ductile shear fracture with failure mode 2. And now let's see in our total map of experiments where we have this conventional failure mode with our plane strain failure and where we have this ductile shear failure. And it's obvious that all the points where we have this significant reduced formability, this shear failure occurs. But now the question, why? What's the reason why we have this different failure modes? And therefore, it's helpful to have a microscopic view in the specimen. And what is done now? Here we see for this 0,0 and the 90 combination, the strain path after the preforming step. So this is a moderate first start of strain. Then we have an ongoing intermediate step, and then finally where we have the failure of the specimen. Here on the right-hand side, conventional view 1B, 2B, 3B, we see nearly the homogeneous specimen. Then after start of diffuse necking, some small voids which can occur, and finally the crack starting out of the middle of the specimen in the well-known representation. But now have the look on the second curve. Again, only difference, 0 degrees preform and just turn around and then the second forming step in 90 degrees. What we see, direct after start of the second forming step, we have voids which occur. That means the start of microvoids is here not caused by a three-dimensional stress state, just due to the texture development based on the preforming step. And this, from our point of view, is the first time that we really can prove that this is an effect leading to different failure modes. Then we have the increase of this microvoiding and finally the fracture. And due to this enormous amount of voids, we don't have the skip into the plane strain behavior. So let's summarize this. Even for this one-phase material, we have based on this texture development a start of microvoiding directly after change of the loading direction. Of course, now someone can say it's a bad material. It's not only a physical effect because we have inclusions of material or something like that. To see if it's really a physical and effect which can occur also for other materials, we used other materials. And here, for example, the IF steel 260, which is one of the purest materials we are using in sheet metal forming, or also for aluminum. And what you can see here, also for this interstitial free material or the aluminum, this effect occurs. So let's see, even after this large pre-strain, for different materials, this shear failure can occur. And of course, as you can see here, it's important if you have forming stages with a big pre-forming and then a second forming step, we should take this into account when we have an accurate forming simulation. But how to do this? As we've seen, it's a texture. We can perhaps use crystal plasticity or other effects, but we know that it's really expensive. And we tried in this paper to start with a well-known way of phenomenological description. Of course, we promoted the GFLC, which is a pure phenomenological model, and tried to extend this by taking these experiments into account. What is the idea of the GFLC, just to summarize? The idea is you have to have a suitable amount of experiments. Here you see in the preforming strain length and the preforming direction that these are experiments which you can use with the Nakajima test. And on all these points, we do post-forming steps, for example, for experiments, where we have a remaining FLC. And the basic idea of the GFLC is just to interpolate this given information to any possible preforming combination of preforming length and preforming direction. But it's still isotropic. And now what we have to do is to add this anisotropic information within the framework of this phenomenological description. Inside the phenomenological model, it's quite easy because you can add a second direction where we have the loading direction or the change with respect to loading, respectively, rolling direction. So that means we have to do experiments on all these points, and then it's possible to interpolate the remaining FLCs, which is measured on every point, just with the same approach functions as we have done this in the GFLC. So you have to do the experiments. You can use these experiments within your phenomenological model, and now it's possible to predict arbitrary combinations of non-proportional and anisotropic material behavior. Therefore, it's now the next step, doing this, of course, how to validate this. And when we want to validate this, you should have also a boundary value problem, which is more close to industrial applications. And this is done in this paper by our so-called MUC test. Of course, it's a similarity to our tone Munich, but we say it's material under control, and that's the combination of MUC. The difference between the MUC test with respect to the Nakajima test, as you can see here, we have a changed binder, a so-called butterfly binder, and punch, also where we have different radii and combination of strains. So there, with this boundary value problem, it's possible to have a more complex strain distribution within the specimen in comparison to the conventional Nakajima test, which you can see here. So we can do these experiments. Here you see a combination 0, 0, 0, 45, and 0, 90. And what's also obvious for this more complex strain distribution, that we have a significant change with the failure behavior. So here, with 0, 0, we start localized necking out of the domes on the left and right-hand side. With the 0, 45 direction, also strain starting here, but we also have a shear failure in 45 direction, and with the 0, 90, we have a shear failure in combination of this inner specimen. So let's summarize this. Also, for this more industrial-oriented boundary value problem, we see also a big change in failure behavior, and also with reachable heights of the test when having the 0, 90, the 0, 45, or the 0, 0 combination. And now, let's use this information to validate our generalized anisotropic GFLC model, our 3D GFLC model. Here you see the surface, which is used based on the interpolation of the experiments. And here we have these points of the 0.45, 0.0, and 0.90 combination. Also in this graph you can see seems to be an accurate prediction. And then we can have a deeper look just with a Gantt diagram, and then we see here the model and the experiments that we really have a very, very good prediction of the failure, even when we have these totally different failure models. So let's conclude our presentation. So I want to summarize again that the change in loading direction significantly influences the remaining formability, change in loading with respect to rolling direction. So also, what was really surprising, that different failure modes can be observed. And also when we have a deeper look inside the material, that a surprising void growth, start of microvoids and void growth based on the microstructural analysis is the reason for that we have these different failure modes. Within the framework of a phenomenological model, it's possible to predict this effect. And also, of course, we want to go on. That means further materials, DP steels, aluminums, and so on will be investigated to see how critical this effect is also in a wider class of used materials. Therewith, thank you very much for your kind attention and looking forward for an interesting discussion.